Around 4 million years ago, the ancestor of humanity, Australopithecus, finally appeared on Earth. Although being called the ancestor of humanity might sound grand, in reality, Australopithecus at that time was nothing more than prey for numerous predators. They were not strong like other animals, couldn't fly like birds, and couldn't swim well like fish. In other words, humans were insignificant animals with nothing particularly outstanding. However, as time passed and humans began to walk on 2 feet, their hidden potential started to reveal itself. In the blink of an eye, humans rose from being prey to predators, and soon they became superior to anything else on Earth. At this point, some scholars began to have questions. If the history of the Earth did not start with the birth of humanity, what existed on Earth before then? Did the Earth also have a moment of birth? If so, what is the nature of the unknown black space that holds the Earth, the universe? These questions have been posed since thousands of years ago and remain a mystery even in the 21st century. Today, let's explore the science behind what is the nature of the universe from the comfort of our room. Let's begin right now. Since ancient times, humanity has strived to find the fundamental essence of all things. Serious research began in ancient Greece, a period when all academic disciplines first flourished. Ancient Greece, one of the most prosperous times in human history, enjoyed a relatively affluent lifestyle compared to other eras. Instead of just seeking immediate sustenance, people began to question fundamental issues such as why humans exist and why they make certain choices in specific situations. Their inquiries eventually extended to the universe itself. Many philosophers put forth numerous theories to explain the world more clearly. Around the 6th century BC, Thales, the first philosopher of ancient Greece, sought the fundamental essence of all things. What he discovered was that the fundamental essence of everything was water. He continued discussions on the constituent particles of matter to understand natural phenomena. As a result, Empedocles proposed the theory of the 4 elements for the first time. The theory of the 4 elements posited that all things are made up of water, fire, air, and earth. About 100 years later, Aristotle developed this theory further, asserting that each of the 4 elements possesses the qualities of wetness, dryness, coldness, and hotness. In summary, water is cold and wet, fire is dry and hot, air is wet and hot, and earth is dry and cold. Looking back now, the idea that everything is made up of just 4 elements sounds quite absurd, but considering that this was an era without basic concepts of matter, it was indeed a remarkable insight. Aristotle also believed that each element had a specific weight and thus a designated place. He argued that the most stable state was when the lightest element, fire, was at the top, followed by air, water, and then earth in that order. However, this seemingly perfect theory of the 4 elements had a critical flaw. It couldn't explain the celestial bodies that continuously moved up and down in the sky. If they were made of fire, they should continuously rise. And if they were made of earth, they should continuously fall. The fact that they moved up and down was inexplicable. Eventually, Aristotle posited that there was an unknown element that caused these celestial bodies to move up and down. He named this 5th element ether. This idea naturally led to the development of the geocentric model, which posited that the universe revolves around the Earth. Until the advent of modern astronomy, the geocentric model was a very convincing theory. It wasn't easy to accept the idea that the Earth, on which one stands with both feet, was moving, let alone the sun rising and setting around the Earth. However, there was a significant problem with the notion that all celestial bodies revolved around the Earth. If all celestial bodies were indeed revolving around the Earth, they should always move in a consistent direction, like the sun or the moon. Occasionally, however, some celestial bodies would set in the west from the east and then, at other times, move from west to east, which was quite strange. But the greatest astronomer of the time, Ptolemy, came up with a theory that perfectly explained this phenomenon. The solution was the concept of the epicycle. In simple terms, an epicycle is a theory that suggests a celestial body orbiting the Earth also makes a small circle on its own path for no apparent reason. During the process of making this small circle, there would inevitably be a moment when the direction reverses, making it appear to us as if the celestial body is moving from west to east. This was the appearance of the universe based on Ptolemy's introduction of epicycles. It seemed quite complex. Surprisingly, however, by incorporating epicycles, it was possible to perfectly explain the movements of all celestial bodies observed in the sky at the time. Mathematically, there were no errors to be found. They finally believed they had unraveled the unexplained phenomena of the universe and discovered the laws of all things, leading to the geocentric model being accepted as the absolute truth in cosmology. However, about 14 centuries later, cracks began to appear in the seemingly perfect geocentric model. For approximately 14 centuries, Ptolemy's geocentric model was regarded as the truth of cosmology, and no one dared to challenge it. In fact, the concept of the heliocentric model, which posits that the Earth moves, existed alongside the geocentric model that suggested the sky moves. As early as the 3rd century BCE, the ancient Greek philosopher Aristarchus had already advocated for the heliocentric model. However, the heliocentric model was not attractive to them. The world was supposed to be governed by simple and clear laws, but the heliocentric model made the depiction of the movements of other planets overly complex and inelegant. But 14 centuries later, the heliocentric model was rediscovered by an astronomer. In the early 16th century, the Polish astronomer Copernicus studied Ptolemy's geocentric model and was amazed at how accurately his theory explained the movements of the sun, moon, and planets. However, something bothered him: the core of Ptolemy's geocentric model, the epicycle. After the telescope was developed, Copernicus used it to observe celestial bodies in the sky and collected data over many years. To explain the movements of these bodies using Ptolemy's epicycles, at least 80 epicycles were needed. While the use of numerous epicycles could somewhat explain the movements, he believed that the universe could not operate in such a complex manner. Moreover, although Ptolemy's model predicted the positions of the planets quite well, there were continuous discrepancies when compared to actual observational data. At the time when Ptolemy proposed the geocentric model, ancient Greek philosophers believed that celestial bodies orbiting the Earth moved in perfect circles at constant speeds. Their interest in the heavens stemmed from their curiosity about celestial bodies moving in circles, so it was natural for them to believe in constant circular motion. Thus, they believed that the sun also orbited the Earth at a constant speed, making the lengths of the 4 seasons always the same. However, measured data showed slight discrepancies. Spring lasted 92.75 days, summer 93.75 days, autumn 89 days, and winter 89.5 days. Ultimately, Copernicus thought that the universe, which should be simple and clear, could not be so complex, and with these discrepancies, he believed it was inconsistent with the harmonious providence of God. Seeking a beautiful cosmological model that aligned with God's will, he developed his own theory. First, he decided to eliminate all of Ptolemy's epicycles, which were both the core and the problem. He then researched what kind of cosmic structure would allow planets to move in perfect uniform motion. As a result, he came up with the extremely shocking idea that all planets, including the Earth, revolve around the sun. This idea is what we know today as the heliocentric model. He realized that the heliocentric theory quite accurately represented the story of the universe, and he developed this idea more concretely, leading to the creation of the book On the Revolutions of the Celestial Spheres. Around 1530, the heliocentric theory was a truly astonishing theory, and once it was revealed to the academic world, it was only a matter of time before he became a famous figure worldwide. However, unfortunately, he could not share this amazing fact with the world. The reason was that the geocentric theory, which had been ingrained in people's minds throughout the 14th century, had a very strong foothold. The geocentric theory, which posited that the Earth was the center, carried the notion that the Earth was an absolute entity, almost like a god. Denying this was tantamount to going against the will of God. Copernicus, being both an astronomer and a devout Christian, found it difficult to reveal this theory to the world. About 40 years later, just before he passed away, this book was finally made public. Naturally, his heliocentric theory was not accepted by the academic world, as it was considered blasphemous, and it was even treated as a banned book. The persecution of the heliocentric theory was quite severe. In the late 16th century, Giordano Bruno was greatly inspired by Copernicus's heliocentric theory. Furthermore, he made a very futuristic claim that the Earth orbits the Sun, and the stars in the night sky are individual suns far away, around which planets like Earth are revolving. Therefore, he argued that it was only natural that many universes existed, and Earth could not be the center of this universe. Up to this point, it was just an opinion, and as long as he didn't boast about it openly, it wasn't a big problem. But when he accidentally mentioned these heretical ideas to a noble while working as a tutor in Venice, things took a turn for the worse. The noble, upon hearing this, immediately sent him to the Inquisition, and he was eventually burned at the stake for his heretical statements. Thus, advocating for the heliocentric theory in the academic world at that time was extremely dangerous, to the point of threatening one's life. However, around that time, there was a great scientist who dared to advocate for the heliocentric theory, despite the risks, the famous Galileo Galilei. He was very curious about astronomy at the time, and was looking at the sky through a telescope. In doing so, he discovered 4 celestial bodies that appeared to be satellites of Jupiter. This discovery alone was sufficient to gain recognition in the academic world, but the problem was that these satellites were orbiting Jupiter, not Earth. Not only did they observe the Moon and discover that it too was a rocky celestial body, no different from Earth, but by observing the movement of sunspots, they shattered Aristotle's cosmology, which stated that celestial bodies were perfect and fixed. Additionally, they crucially found a fatal flaw in the geocentric model. According to Ptolemy's geocentric model, Venus, which orbits closer to Earth than the Sun, could never hide behind the Sun. Therefore, we should never have been able to see a fully illuminated Venus, like a full moon, because the intense sunlight would obscure it. However, strangely enough, we were able to see a fully illuminated Venus, which proved that Ptolemy's geocentric model was incorrect. Besides this, Galileo Galilei discovered numerous pieces of evidence refuting the geocentric model, and eventually, in 1609, he began advocating heliocentrism. Initially, he did not face severe criticism due to his scholarly reputation and career, but his relentless insistence on heliocentrism eventually made him unpopular. Thus, in 1616, the religious trial he had avoided for 7 years finally came upon him. Fortunately, the trial was not as cruel as we might think. The inquisitor Roberto Bellarmino politely requested evidence for heliocentrism from Galileo. However, Galileo had only found evidence that Ptolemy's geocentric model was wrong, and had no proof that heliocentrism was correct. Consequently, he lost the trial. At this time, Copernicus's book, On the Revolutions of the Celestial Spheres, became a banned book. However, the suppression of heliocentrism could not quell the curiosity of scientists. In the early 1600s, Johannes Kepler, a German mathematician and astronomer, decided to focus particularly on Mars among the numerous celestial bodies. He spent 8 years persistently observing Mars and collected all the data. Using this data, he attempted to describe Mars's orbit. Until then, all astronomers believed that whether the Sun orbited the Earth or the Earth orbited the Sun, the orbit would always be a perfect circle. However, according to Kepler's observations, Mars did not orbit in a perfect circle. After numerous rechecks over several years, he finally came up with the idea of an ellipse. Miraculously, this resolved the long-standing problem of Mars's orbit, and in 1609, he announced this fact to the world in Astronomia Nova, New Astronomy. 7 years later, in 1616, he published Harmonices Mundi, the harmony of the world, presenting Kepler's 3 laws, which are indispensable in the laws of the universe. However, even this was not enough to overthrow the firmly established geocentric model, and time passed by ruthlessly. Soon after, a scientist emerged who would finally topple the geocentric model. His name was Isaac Newton. As you know, Newton discovered the universal law of gravitation, which states that objects with mass attract each other. This universal gravitation successfully explained why the Earth could orbit the Sun, finally toppling the geocentric model that had dominated humanity for 14 centuries. Subsequently, James Bradley discovered the phenomenon of stellar aberration, where starlight appears tilted due to the Earth's orbit, supporting heliocentrism. In 1838, astronomer Friedrich Bessel discovered stellar parallax, where the same star appears differently depending on the observer's position, providing decisive evidence that the Earth orbits the Sun. Thus, The cosmology that began in the 6th century BCE finally concluded with heliocentrism over 2,000 years later. However, this only revealed the relationship between the Earth, the Sun, and the other planets, leaving their origins still unknown. Yet, about 100 years later, the greatest genius in human history would be born, who would solve even this mystery. In 1905, Einstein gained worldwide fame by publishing his theories on the photoelectric effect, Brownian motion, and special relativity. The 3 papers he released during this period were groundbreaking discoveries that formed the foundation of modern science, making 1905 known as the Miracle Year. But Einstein did not stop there. In 1915, he published a historic paper that sought to uncover the fundamental nature of the universe, or rather, the fundamental nature of everything. Yes, it was the general theory of relativity. Among the vast amount of information contained in this theory, the most important was the equation known as the Einstein field equations. This equation allowed for the calculation of the curvature of space-time based on the distribution of matter, offering an ultimate equation to uncover the fundamental nature of everything humanity had been seeking for ages. If one could fully solve this equation, it would provide access to the essence of the world that had plagued humanity for thousands of years, and even explain why and how the universe was born. However, Einstein arrived at a slightly incorrect conclusion with this equation. At that time, scientists believed that the universe had always been, and would always remain unchanged, maintaining its current form for millions and billions of years. It seemed like common sense, as looking at the sky today, tomorrow, or even a year from now, one would not easily notice any immediate changes. However, contrary to this common sense, no matter how Einstein tried to interpret his equation, he could not obtain a static universe as a result. But since the prevailing belief was that the universe neither expanded nor contracted, he eventually introduced the famous cosmological constant to correct for this slight discrepancy. In 1917, using this, he published the paper Cosmological Considerations in the General Theory of Relativity, bringing him a step closer to the fundamental nature of the universe. However, in 1927, a Belgian scholar named Georges Lemaitre concluded that according to Einstein's equations, the universe must be expanding. But at a conference in Brussels the same year, after hearing Lemaitre's presentation, Einstein remarked, "Your calculations are correct, but your physics is abominable." Thus, Lemaitre, who was still a novice in the academic world, seemed to be dismissed by Einstein's disdain. However, in 1929, an astonishing observation by American astronomer Edwin Hubble, who was observing celestial bodies, discovered that the objects he was observing were moving away from him. The fact that celestial bodies were moving away could only be explained by the expansion of the universe. This moment validated the idea proposed by Lemaitre in 1927 through observational evidence. Consequently, Einstein had no choice but to retract his static universe theory and the cosmological constant. But what Lemaitre had actually intended to convey was not just that the universe was expanding, but that if time were reversed, the universe would have contracted, and ultimately, if rewound far enough, the universe would have started from a single point. This is what we now call the Big Bang. However, while the expanding universe could be accepted as an observational fact, the notion that this vast universe originated from an inexplicable explosion from a single point was hard to believe. Questions arose about what could have caused such an explosion, and how powerful it must have been to create such a universe. The Big Bang theory was so revolutionary that it was hard for scientists, who had believed in an unchanging universe, to accept. As a result, some scientists who could not accept the Big Bang theory acknowledged the expansion of the universe, but could not accept that it started with a Big Bang. They proposed the steady state theory, where the universe expands. But to fill the expanding vacuum, extremely small amounts of hydrogen atoms, undetectable by humans, are spontaneously created. This idea seemed absurd, ignoring the law of conservation of mass, but it underscored their inability to accept the Big Bang theory. However, in 1964, while observing the universe at Bell Labs, astronomers Arno Penzias and Robert Wilson encountered a strange noise in their detector. Initially, they thought it was due to dust or birds interfering with the signal. But even after eliminating all variables, the noise persisted. This noise was actually the cosmic microwave background radiation, uniformly spread in all directions in the universe. This provided clear evidence that the early universe, following the Big Bang, was extremely hot, around 3,000 degrees, and that matter was distributed in a highly uniform state without the formation of galaxies or stars. Thus, the long quest to understand the essence of the universe was finally realized. But what exactly was the Big Bang, which is considered the essence of the universe? What happened immediately after the Big Bang? And how did a highly dense point create this vast universe? The next topic we will explore in our series is, what was the beginning of the universe like? This has been Science from the Room.